So good afternoon, everyone. My name is Ido Diamant. I'm a bioinformatics software engineer in the Mayan Lab at the Icahn School of Medicine in Mount Sinai and a member of the CFDE DRC. And today I'm going to talk a little bit about the process of creating Croissant files for CFDE datasets. I'll start with an introduction about Croissant, which is a machine learning metadata format to describe datasets that are ready to be introduced into machine learning pipelines. It's a format that was developed by researchers at Google to define machine learning ready datasets in a unified format and make them portable and interoperable. It's important to note that Croissant doesn't change the formatting of the data, but it just describes what data is available and how it's structured and where it's accessible. It's based on the schema.org metadata description for datasets, and it adds a few new properties and modifies a few of the existing ones with machine learning applications in mind. And it's created with both data creators, data repositories, and then machine learning workflows in mind, as we can see here on the right in this diagram from the paper and the GitHub repo. So Croissant describes datasets in four different layers. The metadata, which describes the dataset itself, including responsible machine learning aspects, which I'll touch on in a few slides. Resources, which are one or more files where the data in the dataset actually is located. Structure, which is how the raw data is formatted and how it can be accessed by these machine learning workflows and frameworks. And then semantics, which is how the data is most often used in an ML context, including data typing and split and train test splits. So the process to create a Croissant JSON for a dataset basically is to go through each of these layers and to fill out the required properties so that someone can access the dataset using this Croissant JSON format. So the intended applications of Croissant, again, are for these machine learning ready datasets. It's meant for data that is a few lines of code away from being used as data or labels in an existing pipeline. We can see here in an example from the supplementary information for the paper, loading in a subset of this COCO 2014 dataset, which is objects and images in context. And they are ready to be used as training data after just a few lines of manipulation. So I'll touch on the integrations here, which are both from the dataset repository side, from Hugging Face and OpenML and Kaggle. These integrations are meant to make these datasets that are described in the Croissant format easily discoverable and portable. So users can search for datasets, and if it fits with a workflow that they have in mind, these datasets are easily discoverable. And then on the other side of things, these machine learning workflows, machine learning frameworks have these integrations with their data loaders, which makes it very easy to access data that is described in the Croissant format with, again, just a few lines of code that can load it into the format that's expected by the ML pipeline. And then the last thing I'll touch on before we get into an example is this responsible AI specification. These are all new properties that are optional to include, but address some use cases that might be useful for creators who are picturing how their data sets will be used, including the data lifecycle. If data becomes outdated, it may be useful to note that like a new version is available, or it only includes data up to a certain date. And these regulatory and compliance issues where there may be a specific license that's the data is accessible under, and it may be only valid for some use cases, as well as giving some deeper insights into how it's been manipulated and processed in the past. So again, these are all optional properties, and they build on the schema.org dataset properties and modify some of the Croissant ones that are included. But they are useful to think about when constructing these. And then that brings us to the current state of CFD Croissant datasets. So earlier this year, we created 13 Croissant files detailing CFD datasets from different DCCs. These were previously processed for the Harmonism resource developed by the Mayan Lab, which includes metadata from the original data set as well as this processed data in a format that's ready for machine learning. So we bundle together this metadata and data description to create these Croissant files for these 13 data sets. But in the future, we are hoping to continue expanding this effort, and we can continue to add to the number of data sets that are already available in the data portal and the CFD workbench. Now that we've had a little bit of an intro, we'll get into an example of developing a Croissant file for a dataset by following along an example from the Rumagio drug perturbation signatures dataset. We'll be doing this using this Croissant creation notebook that I developed, which basically goes through the process of detailing information for each layer for a dataset. And then at the end, we'll combine all of the layers together and export it into one Croissant JSON file. So a little bit of info about the dataset that we'll be looking at. This is the Rumagio drug perturbation signatures dataset, which is a subset of Rumagio. Rumagio is a resource that was developed by the lab that generates differential expression signatures by identifying groups of samples from geostudies with a shared condition and performing differential expression analysis. Subsets of the Rumagio resource were used to create a gene perturbation dataset and a drug perturbation dataset by using a list of drug names compiled from a few different resources and the Rumagio API. These were, again, previously processed for harmonism, so we have the data formatted in a data matrix and the associated metadata attached, which we'll use to create this JSON file. So again, just an outline for this, we'll be going through the Croissant specification, which details all of the required properties to create a valid Croissant JSON LD file. We'll construct the metadata resource structure and semantics layer for the dataset using the ML Croissant Python package, which was developed by the same team that wrote the specification. And then once all the layers are defined, we'll assemble them into one object in the ML Croissant package, which then will generate a JSON file for us to easily distribute the dataset. So the installation process for this is very simple. It's just a pip install, and then we'll just import it in our notebook later. So I'll start by going over what we need to define the metadata layer. So for this, some of the properties, the name, description, license, URL, we'll take directly from the dataset. We'll just outline what the dataset is, where it comes from, where people can find it, and how it is allowed to be used. For the creator and date published, we also have that information from when we created the dataset earlier this year. And then these last two required one, the context, type, and conforms to properties. These will be handled by the ML Croissant package when we assemble the dataset later, and we actually don't need to worry about defining them individually. There's also a number of recommended properties. These are not required, but can be useful again for discoverability and transparency. We'll include the cite as property here, which allows us to cite a publication where that is associated with the dataset. We'll use the Rumagio publication. But note for some of these, you can include many options. In this case, we can only include one publication to conform with the specification. So if there's a data set that may be related to multiple publications, it might be a good idea to use either the landmark publication or the most recent one that describes the subset of the data that's being described. The specification also details this version property, which they recommend using a major minor patch version format, where major describes a change in the data itself. A minor will describe some change in how the data is structured, and then a patch will be a small change, usually something in the way the data is serialized or something similar to that. So for the Rumagio dataset, for the metadata layer, we'll describe again using the name and description that we've gathered when creating the dataset. We have the publication from last year, which we'll describe here in BibTeX format, which is recommended by the specification authors. The creators and date published from the dataset, which we again have from when we created it earlier this year. And then our version, URL, and date published. So later, this is skipping forward a little bit, but once we've assembled the data sets, this is what the finished JSON will look like. We can see the type and conforms to properties that I mentioned have been included in this, and we don't have to worry about them. The context is also generated in this case, but this formats and includes all of the necessary references in our uh, JSON, so the package can handle the sort of complicated parts of this for us, rather than if we were doing it manually. Next is the resource layer. The resource layer contains the distribution property of a schema.org dataset, and it has to describe one or more record file objects or file sets, which define where the data exists. So the distribution property is required, and then within this, we can include a number of files. Um, we have to specify both the name and the URL for this, so where it can be accessed. And then there are a number of other properties that can be included. For example, a SHA-256 hash to make sure that the data integrity is maintained, as well as this contained in, which lets us specify if we have an archive or something like that a file is a subset of another file. And then the file set is more useful for a number of files that share the same format. This is useful for something like an image data set where you have a number of PNGs that have the same formatting, but it's less useful for these like matrices that we'll be working with. So for the Armaggio distribution, our file is at this URL, and we can see just from the file structure that it's a txt.zip file. So we have an archive and a txt file within it. So we need to define two file objects. In this case, we'll define the attribute table archive, which has the zip encoding format, and then contained in that is our attribute table, which is in this txt format, which is a tab separated value matrix. So again, once we have gone through and assembled everything, this is what our formatted JSON will look like here on the bottom, where again, a lot of the context and references are taken care of for us by the package when the JSON is assembled. But we can see the content URL and hash fields have been populated, and we have a reference in the contained in section of the attribute table file that it's contained in this archive. The next layer we'll cover is the structure layer. This covers the layout of the file. So in this case, we'll describe a record set, which is made up of one or more fields. In this case, our fields are going to be our columns in the matrix. So these describe how a framework will be able to load in parts of the data that are going to be used for training or labels. So I'll go into a little bit of our detail about our fields. We need to describe a source, a name for the field in the description. Um, these will tell us sort of what differentiates the different fields from each other and what file object or source they come from. So looking at our attribute table from the Armaggio dataset, if we load this in, we can see that we have our genes as our index here, and our column names are our drug perturbations. So what we'll do is we'll define a field for our index and a field for each column. So when the data is being loaded, it will be able to associate the genes with our index again, and each of the columns will be treated as a feature. So to create this, we'll define a field again for each column. For our index column, we'll use the optional key specification as well to indicate that it's our primary key for this matrix. We'll also include some metadata from this additional file. There are a number of ways to do this, but in this case, we'll just add the drug perturbation metadata in the description, which provides a slightly more useful context to the user rather than just the name, which uses some of the internal groupings from Armaggio. So in this case, we'll elaborate a little bit and include what the conditions actually are in the description of each field. So again, we have one field created for the genes and then one for each drug perturbation column. And then after we've done that step, we'll define all of our fields in a record set, which we'll call associations here, but it can be changed to whatever describes the data best. And then within this, we'll describe our fields that we created in our last step and the key column as well. Um, and then again, looking forward, once we've assembled all of the data, this is what our JSON will look like on the right. So we can see we are a list of fields, which each of which has this type, name, description, and the file object that it comes from, as well as the column name of that file object where the data will be gathered from when this is loaded into a records from a dataset loader. And then the last layer we need to define is the semantics layer. Um, this layer has some of the most leeway. Not every dataset will need to define every part of this. Um, But some useful features that are added in this one are data types, where we can use some of the atomic types that are defined, or more complicated ones that can be imported from a schema.org specification or defined in a custom way. For example, on the left, we have this geocoordinates data type, which expects a latitude and a longitude. So you could define a field having that has a number in it as a latitude and a number one as the longitude. And together, those two fields will make up this geocoordinate type. You can also define train test splits like we see in the middle, where you can section off parts of the data to be training, validation, or test, which makes machine learning experiments very reproducible if they're described in this way. And we can also add some data labels, for example, for categorical variable types. On the right here, as we see with this animal or person type that can be defined for each feature or for each sample. In this case, we don't need to include all of these for this data set, but we will include the data type. So for each field from our previous step, we're going to add in this um, data type text for our gene symbols and data type integer for our attribute for our perturbation values for the associations, which in this case, since we have a ternary matrix, will be either 1, 0, or -1. But if we were describing a matrix with continuous values, we could replace this with a float or something similar. Um, and again, various data types can be used to describe a data set depending on what's contained within it. We'll also include this is array property and array shape because we know the size of our matrix. Again, this is not strictly necessary, but it could be useful for someone who's using the dataset later on. Um, okay. So now that we've defined our information for each layer, what we'll do is we'll create this metadata object using the ML Croissant package, where we'll put in all of the information we've defined in our previous steps from our metadata, our distribution property, which has our files, and our record sets, which has all of our fields and structural information. At this point, one nice feature of the package is you can print out any warnings that show up when you produce this. So if you're, say, missing a required property, like if you forgot your hash for your file object, it'll give you an alert here before you proceed any further and give you a chance to correct any missing properties. Um, Finally, once everything is all set, we can just dump the metadata object that we've created here with the package to JSON, and we'll have this dataset JSON all set and properly formatted. Um, at this point, if we take this, we can use it in a number of contexts. So if we bring this over to another notebook where we want to do some machine learning workflow, we can load it in simply with the ML Croissant package again using this dataset object this time, which we feed in a JSON-LD file from a previously built Croissant dataset. Then we can extract our properties from the metadata field, the content URL. We can get our extract property, which is, again, how we defined which columns should be used from the matrix. And if we download the matrix that's described and unzip it, then we can read it in with a tool like Pandas, just for visualization here. get our extraction columns and set our key, and then we have our matrix in exactly the same format in just a couple lines of code. And this could be, we could get this same format from different data sets, even if they're originally formatted slightly differently. If they're described in this way, we can make sure that all of our input data is now aligned to the same format. Uh, this is how we would do this manually. The ML Croissant package also has its own method for loading in data sets, which can be kind of slow for larger data sets with millions of records, but is reasonably fast for smaller ones. And then, as I mentioned earlier, also these dataset loaders for the various ML frameworks have these built-in integrations, which can also use this Croissant file to create a dataset in their respective formats. So just to conclude, we've seen how the Croissant format can be used to describe datasets that are ready to be integrated into these ML workflows. We've seen the layered approach where we define our metadata resource structure and semantics using the ML Croissant package in a programmatic way. We've seen some of the fields and extensions that can be added to the specification to make the format more richly detailed and address various use cases and various types of users. And we can ensure that our datasets have been described in a unified format that makes them ready to port into a machine learning pipeline very easily, regardless of where we're getting the dataset from or what specific framework we're using to load it in. With that, these are a number of additional resources that may be useful. There's the Croissant paper and then the Croissant and RAI specifications. These two are included in all of the Croissant JSONs that are created. There's also the GitHub repo, which has the Python package and a number of other resources. There's the Hugging Face Croissant editor GUI, which kind of like the notebook allows you to create a JSON file programmatically for a dataset by defining each part. But it can be slightly rigid for because it's a GUI, it has some limited options. Um, and then there's the CFDE Croissant Creation Notebook, which I've kind of stepped through here, which is on Google Colab and easily modifiable to different data sets that you may want to create. With that, I'd like to acknowledge all the members of the Mayan Lab, especially Javi Mayan, the PI, and everyone else who has helped contribute to this project as we've developed it, and to all of the members of the various CFDE DCCs that have developed data and worked with us to get these loaded onto the data matrix. Thank you.